really is just a test of, were you paying attention the last 15 minutes? Or maybe more properly, was I making any sense? Because this is exactly what I was just talking about in the street example. What's the problem? Yeah, I see your hand, but you already got to answer something. So, yes? Malloc and free are not in the same place. So once again, I have this, and I know it looks like, well, what's the big deal? I mean, geez, they're on the same screen, they're on the same slide. But you just have to use your imagination, is that programs are huge. I mean, it's like the implementation of Facebook, I think it's like 100 million lines of code. And somewhere in that 100 million lines, there's a module that does the malloc, and someplace else, you call it, and you forget. So easy. So what's a better way? Yes.
You both the one being copied and the one being copied to are on the same.
Right. So I think what you said is just what I showed you previously, that I'll move the malloc out of copy into foo. So you'll see now what foo does is it the second line, it does the malloc. Same exact malloc, I just moved it here. And then it calls copy and passes now two pointers as parameters, the destination and the source. Previously, you just passed one, just the source. And the destination was returned as the result of calling copy. Now copy doesn't return it. And now I say, print whatever I'm doing, I say free. And this is better because foo does the malloc and the free. I can look at copy and say, copy can't possibly cause a memory leak because it doesn't allocate anything. So I'm very happy as the person who wrote that module. If there's any bug in this program, it's your fault, not mine. Okay? The concern has now been isolated into a single module. Now this is a harder question. There's something wrong with it. This is the attack vector. This is the most common mistake, and the most costly mistake, the most common costly mistake that humans have ever made. It's just right there. And it's a little bit easier to see. That is perfectly fine. There's no bug there. But that's actually not, when I write copy like that, so that's not how it's usually used. This is how it's usually used. What you do is you allocate a buffer of some capacity. So the top one is using malloc, the bottom one is using the stack. They're the same except for that feature. We'll just look at the top one. I've decided to have a buffer of 1024, a quarter of a page of data. Doesn't matter, kilobyte. So that's how big these are. Now I call copy, and I print out what's there, and then I call free. Right? Only thing that's changed is the size of the allocation. And I might be doing this, for example, in a web browser, where what I'm doing is I'm copying the URL. And the browser spec says that URLs have a maximum size of 1024 characters. So I read the spec and said, well, how big do I need to make this buffer? Well, 1024, because URLs are not allowed to be bigger than 1024. Now, there's something horribly wrong here. And I don't want you to tell me. I want you all to discuss this. And I want everyone to find it. Single most costly. If we just knew about this, I mean, it is actually billions of dollars, trillions of dollars. US dollars. Okay, so who sees the problem? Raise your hand. I'm not making waves. Anyone else see the problem?
Do you set the last one to null?
Well, no, I'm copying length plus 1. So the copy is actually correct. It's a good idea. But if I just went to length, then I wouldn't copy the null, but I'm copying the null.
Length string is bigger than the null.
Exactly. So what happens if, so here is S. And here's D. And that's 0, and that's 1, 0, 2, 3. All right, that's what I allocated. I allocated 1024, and I allocated 1024 because the spec says URLs are never bigger than 1024. But what if the string is bigger? What if I don't get a 0 until way down here? Okay, does everybody see that? So if you looked at this, you would see characters in here, none of which are null. So you just keep going, and the length of the string is bigger than 1024. What does copy do? Well, copy is 0 is 0, and 1 is 1, is 2, 123 into 123. 124 right here. 125 right here. It copies all of this into memory after there. Does everybody see that? Why is that bad?
We're accessing out of the bounds of what we've actually allocated. So
Right.
behavior.
Yeah, exactly. And what would be a really bad possible actual behavior?
You might overwrite
Right.
something.
So you might overwrite something that's important. And so this string might override some memory, corrupting memory. It's very much like the dangling pointer problem. Remember the dangling pointer problem was they have a pointer that's a stale pointer into an object that was allocated after this one was free, and then I use this to write into random memory. Well, here again, same thing. I'm kind of writing into random memory. It's like memory you're not supposed to access, but I've just written over top of it. And what have I written over top of it with is this string. So if that string was a URL, who controls the URL that your browser uses? Who could control it? So I make a web page, and I put a link on the web page. And in that web page, I have a URL that is, say, 2,000 characters long. Who controls the length of that string? Me. All I have to get you to do is to click on that. And now your web browser has a source string that's too big. And I decided it was too big. And I decided what was going to go here. So I now have, the bad guy, have written, caused your web browser in the copy routine to write into memory something that I decided what it is. And of course, you can guess, we'll come to the specific example. This is the virus. I just get you to copy it into memory. And if I'm lucky or if I'm smart, I copy it in a way that gives me a sort of form of control over your browser. The bad guy from the outside. So that's why this is bad. So how would we solve this if we just looked at copy? What's a solution? Improvement for copy.
That determination thing, I is less than like.
Right. So what do I need to know? Well, that's exactly right. So what I want to do is stop copy. Doesn't matter how big S is. I want to stop when it gets here. So what do I need to know in order to do that?
Length of both of them?
Yeah, not the length. Remember, there's a difference between length and size. So I can determine the size of this just by calling string length. But what do I need to know in copy? Sorry, I can determine the length of that. I need to know the size of this, D. Is there any way for copy to know the size of D? No, it's dynamic. So therefore, it must be a parameter. That was the first thing we did. Right? It must be a parameter. So this is the correct way. So essentially, any time that you take an array as input and you're going to write into it, you should also, especially if it's a string, you also take the size. So if you look at copy now, and you assume that D size is the size of the destination buffer, then you look at that code carefully, you'll see that it will not copy past the end. And in fact, it's going to stop one before the end so that it has room to write a null. And so now, the implementation of copy can't cause the problem all by itself. It must be the case in foo if you would make a mistake. So in foo now, you'll see that when it calls malloc with 1024, and it passes 1024 as the size of the destination buffer. Now, if you screw that up, if you put 2000 there, then this problem reoccurs. But now that the problem is created by what probably is a relatively easy problem to spot in foo. Does this make sense? Okay. So the standard string library has an addition, so there's string length. Gives you the length of a string. There's also something called string end copy, which is sort of like this, except that it doesn't ensure that there's going to be a null. And it was a huge mistake. And when they realized this, oh no, what do we do? We've already used the name string end copy and has certain semantics. So they created something called string L copy that actually is this. So copying strings, please always use string L copy. Never use string end copy. There's also string copy that was the first one. Don't ever use that. Or not the first one, but the one right before this. And then there's another one, string dupe. So string dupe is the very first one. So string dupe will do the malloc. It duplicates the string. So most common time you're manipulating strings, you're going to use string L copy and have the malloc and free in your little local procedure. Okay. This was from last year, right at the time, last term, right at the time I was doing this. There's a security vulnerability in macOS. I could go find another one. It's like there's an infinite supply of security vulnerabilities, and if you read this carefully, you see a remote attack may be able to cause unexpected application termination or arbitrary code execution description out of bounds read was addressed with improving. Right, so that's it. There was an out of bounds error. It's this error, this bug, exactly. And it caused the attacker to be able to execute arbitrary code in your operating system. Unless, of course, you're like Russia or NSA, something. And they want, because if I can get your operating system to execute arbitrary code, I can learn your password, I can learn all your passwords, I can get you to run programs for me that do arbitrary things. Right? That is really bad. It's called getting the rootkit.
This also how fgets and gets is different, right?
Fgets and gets. So fgets is using a file buffer, right?
Yes.
Gets is just using a string. I don't remember, is there a length? Maybe. They're also different in another way.
Fgets is the length.
Yeah, okay, and so getS is just a string.
Yes.
And this is getting input, yeah. Right, so the input's bigger than the string buffer, yeah. Excellent. All right. So that's what you should do for the simple case of allocation, where you've got one procedure, allocate something, gets people in other parts of the code to do stuff with it, and then I free it. And what was really important there is that anytime I pass one of these pointers to any procedure, it doesn't save a reference to it. So I know when I'm done, I can free it. But that isn't the only story here. The sometimes is you need to sometimes save a pointer that you passed. So this was the problem we started with, where we have foo calls received, I'm back to that formal receive, but that doesn't matter. And then you call bar, and then you call free. And the problem is that bar might save this pointer in a global variable. And if it does, then foo cannot call free, because if it calls free, that global variable is now a dangling pointer. But on the other hand, it might not do that. And if it doesn't do that, then it must call free. Otherwise, the program has a memory leak. And so in foo, to know whether to call free, you have to know what bar is doing. And we want that to be private. We don't want to create the semantic coupling between foo and bar. So next class, we'll look at a strategy to deal with this more complicated thing. Good luck with your, those of you in 221, good luck with the exam. And hurry over there to class.